Hi everyone! In this video we're going to learn about logarithmic functions. Simply put, a logarithmic function is just the inverse of an exponential function. But let's look more closely into this. Recall that the exponential function has the following form: y equals a to the power x, where a is just a positive real number that's never equal to 1. And the power of a, or exponent, is the variable x. It's also important to know that the exponential function is 1-to-1. Recall its graph, it definitely passes the horizontal line test. That means that the exponential function has an inverse. Remember that to find the inverse of the function, we simply have to interchange x and y. That means that the inverse will look like this: x equals a to the power y. And a lot of times when we have to find the inverse of a function, we want to put the function in a form where y is by itself. But how do we get y by itself from this expression? If you think of any basic algebraic operations, none of them are going to work. That's why we have a special function or notation to express y by itself here. And this is how it's written. It can be read in a few different ways: logarithm with base a of x, logarithm of x with base a, or base a logarithm of x. And the notation is such that we put three letters, log. Number a is written as a subscript. It's smaller and lower than the rest of the symbols. And then we have x. And what's important to note here that the roles of variables x, y, and number a are the same as here in this exponential form. In the exponential form, a represents the base and it's a real positive number. Y represents the exponent. And x is the result of taking the base and raising it to the power y. When we switch to the logarithmic form, all roles are preserved. Y represents the exponent, a represents the base and it's called base, and x is still the result of taking base a and raising to the power y. And overall, we can see that logarithm itself, with its base and x right next to it, represent or equal to a power. Keeping all this in mind will help us successfully work with logarithms. And since the inverse of any function is also a function, here we're looking at what's called logarithmic function. Here it is, the logarithmic function. And notice that all the restrictions that we had for base a in the exponential function are still true for the logarithmic function. The base is positive and never equal to 1. However, we have one additional restriction here. It says that x should always be greater than 0. Why is that? Remember that in the logarithmic function, x represents the result of taking base a and raising to the power y. We can see it better over here in the exponential form. But since base is always positive, then no matter what y value we use, the result of this operation is a positive number. Let's practice how to switch from the logarithmic form to exponential form and back. In this example, we have to rewrite these logarithmic equations using an equivalent exponential form. The first equation is logarithm of 8 with base 2 equals 3. To obtain its equivalent exponential form, we need to remind ourselves the roles that all these numbers play in this expression. So 2 is the base of the logarithm, and it will play the same role in the exponential form. With logarithm equals to, always represents the power, and the number or expression that's then inside the logarithm I like to call the result. In other words, to obtain the exponential form, we want to take the base, raise it to the power, and set that equal to the result of the operation. In other words, we're going to get 2 to the third power equals 8. And by the way, this helps us to see that the equality is true. Let's try it with the next equation. We'll take the base 4, raise it to the power 2, and set that equal to what stands inside the logarithm. In other words, we'll get 4 to the second power equals x. Notice that inside the logarithm we had variable x. So altogether, this creates an equation that can be solved. And the step that we just did, rewriting the original equation as an equivalent exponential equation, allows us to find the unknown value of x. X equals 4 to the second power. So I can add another line and say that x equals 16. And finally, the last logarithmic equation here, we'll repeat the steps by taking the base 2, raising it to the power, which is -5, and set it equal to the result, which is 1 over 32. And the exponential form makes it easier to check that this statement was true. In the next example, we're going to try this in reverse. We're going to take these exponential equations and rewrite them as logarithmic expressions. Let's try. I'll start by writing log for logarithm. Base of the logarithm is the same as the base of the exponential expression, so it's 6. Logarithm always equals to a power, so I'm going to set it equal to 2. That's the power in the exponential expression. It means that 36 will be placed inside the logarithm, and that's the result of raising 6 to the second power. So that's the equivalent logarithmic expression. For the next example, example B, I'll place log for logarithm. The base in exponential form is 3, so that's going to be the base of the logarithm. The result of raising 3 to the power -4 is 1 over 81. That's the number that will be staying inside the logarithm. And logarithm itself will be equal to the power, which is -4. And that's the reminder of what we're doing right now. And let's try the last example. So logarithm, log, with base 7, that's the base in this exponential expression, of 1 equals 0. That's the power, or the exponent. And from the last example, we can see that logarithm can be equal to 0, because again, it equals to an exponent. But we can also generalize this case. We can say that no matter what base is, if I have 1 inside the logarithm, then that logarithm has to be equal to 0. And this is because no matter what base is, to obtain 1 as the result, that base has to be raised to the power 0. If a logarithm contains 1, then no matter what the base is, that logarithm will always be equal to 0. Base, power, the result. Next, we're going to look at two special logarithms. They're called natural and common logarithms. A common logarithm is the one that has base 10, like this. However, common logarithms have special notation. Logarithms with base 10 can simply be written without the number for the base. In other words, if you see or use a logarithm without any base written, this automatically indicates that the base is 10. A natural logarithm is the one that has number e as its base. It's a famous irrational number, like number pi. It's called Euler's number, and it equals approximately 2.7. Natural logarithm has its name because it occurs in natural situations from life sciences that involve growth and decay. And as a common logarithm, the natural logarithm has also special notation. Instead of writing logarithm of x with base e, we can simply write ln of x. The ln part is equivalent to logarithm with base e. Let's practice notation for both common and natural logarithms. In this example, we need to rewrite each expression as exponential or logarithmic equation. For example, the first one is ln of x equals 3. This equation is written in logarithmic form. So we want to rewrite it using the exponential form. For that, I have to take the base of this logarithm, which is e, raise it to the power. Remember, logarithm always equals to the power. That's 3. And set it equal to what stands inside the logarithm, which is x. E to the power 3 equals x. That's an equivalent exponential form. Part b is written in exponential form, so we're going to write it as the logarithmic equation. Here I can see that the base is 10, so logarithm will have base 10. And remember, when logarithm has base 10, we don't have to write down the base, so it's going to be just log. Logarithm always equals to the power, so that's 7, and inside the logarithm we have the result of raising 10 to the power 7. So logarithm of x equals 7. That's an equivalent logarithmic form. In part C, we have equation in the exponential form. We're going to rewrite it using logarithm. Base here is e, so it's going to be logarithm with base e, which has special notation ln. Logarithm equals to the power, so I place x on the other side since that's the power. And the result of raising e to the power x will be placed inside the logarithm. Here is an equivalent logarithmic equation. In part D, we have logarithm without any base written. That means that it's base 10. To write the exponential form of this equation, I write base 10, raise it to the power 3. Remember, logarithm equals to the power, and set equal to what stands inside the logarithm, 1000. So we'll take base, we raise it to the power, and set equal to what stands inside the logarithm. In part E, we have ln of e equals 1. This is logarithmic form. To write the exponential form, I'm going to take the base of the logarithm, which is e. I'm going to raise it to the power, which is 1. That's what logarithm equals to. And I'm going to set it equal to what's inside the logarithm, which is e. And here I can verify that this equation is true. E to the first power is e. And we can generalize this example. What we can see here is the case when the base of the logarithm is the same as what stands inside it. The base of this logarithm is e, and inside the logarithm we have e. Such logarithm always equals to 1. This is how we can write it in general. Logarithm of a with base a equals 1. We can easily check that if we rewrite this logarithmic equation using exponential form. I can see that if I take base a, raise it to the power 1, I will get a. Once again, every time you have a number inside the logarithm that matches the base of that logarithm, then logarithm itself will be equal to 1. And for that same reason, ln of e equals 1. And in our last example, we have exponential equation, 10 to the power 2 equals 100. To write down the equivalent logarithmic form, I put log that has base 10, which means that I don't need to write down the base. The result of raising 10 to the second power is 100. That's values inside the logarithm. And logarithm itself equals to an exponent, or the power, which is 2.